Hello, in this video, let's review some of the digital gates and look at a little bit of digital design. So before designing digital systems, let's look at some of the concepts typically of what is known as abstraction in design. We'll also look at the few basic logic gates and look at their truth tables, etc. This is mostly a video just to revise your concepts. And we'll spend some time talking about the figures of merit of digital gates because that will be important through the course. So first thing I want to talk about a little bit is abstraction. So abstraction is a very critical technique, and what it essentially boils down to is hiding the details of the design that are not important, right? For example, if you think about a digital system, depending on your area of expertise or depending on where you think you can contribute, there are different levels of abstraction, if you will. The lowermost level is at the semiconductor level, where you understand how electrons move, what's the physics of electron movement, etc. The level above is the device level, so this decides the process technology, this decides how you're going to make transistors, the other peripheral devices in the structure. The level above, which basically deals with circuit topologies that are very sensitive to device parameters, would be analog circuits, so amplifiers, filters, etc. fall in that. Digital circuits tend to be a little bit forgiving when compared to analog circuits, and so digital circuits tend to have a lot more abstracted values out, and so tend to be further away from the device level. And then you have the logic level, which deals with logic blocks, so that would mean adders, memories, etc. Above that would be the microarchitecture level, which deals with what is the data path design, controllers that are present in to control the flow of data, etc. And then at the architecture level, we talk about instruction sets, register design, etc. Finally, we then enter the realm of operating systems, which talks about device drivers. How do you access this architecture from the code? And finally, you talk about application software or programming, right? So you can be at any level, at different levels of abstraction, you can design the system. Now, when you're working at one level of abstraction, say if you're working at the digital circuit level, it's good to know something about the levels above and below. And the reason being is that changes at either levels tend to impact what you're designing, right? So while you might be proficient in digital circuits, it's a good idea to know what do you do at the logic and the architecture level, even up to the operating systems level, as well as know how to build devices and what its impact would be on your performance. On the other hand, I would also like to warn that you need to exercise discipline, because many a times what happens is this has a certain realm of design, right? And if you want to work productively at any level, you should also understand what are all the design choices available to you, and more importantly, what is not available to you. For example, if you work in a company, say, which does not have a foundry, then playing around with transistor layouts, playing around with transistor performance is something that is not available to you as a digital circuit designer or as a logic circuit designer, which means you need to work with what is available with you. So understanding the limitations will also help with improving the productivity at the level you're working in the design. Now, a couple of principles that apply to hardware design. The first one is what is known as hierarchy. Digital designs typically divide the system into modules and keep further dividing these large modules into smaller modules, etc. So what happens is you can keep going from a much higher level or a much bigger module all the way down to pieces that are very easy to understand, right? And this helps with putting together a block. It also helps with maintaining some sort of a control on your design, if you will. The other important aspect of design is modularity. That is, when you design these individual modules, these modules must have well-defined functions and interfaces. That is, you should be able to clearly specify what is the input, what is the output, and how is the input related to the output. And they should connect without any side effects. That is, once you've designed the modules, it should not impact what is connected before the module or after the module, right? So the performance of the module should be purely determined by what is inside and not what's outside. And finally, you want to think about regularity. That is, you want to seek uniformity across modules. And the reason is when you do that, you can reuse common modules. So it saves a lot of cost and effort during design. And so it's important that when you are designing a large digital system, you pay close attention to these three parameters, namely hierarchy. Your design should be hierarchical, it should be modular, and it should be regular. So let's review number systems. So what are binary numbers? As we spoke in the previous video, bits are represented with values 0 and 1, and they're joined together to form binary numbers. So if you look at a decimal number, it has 4 digits, then you have the ones column, tens column, hundreds column, and thousands column. So each value here has a place value, if you will. Similarly, in the binary system, instead of being orders of 10 in the decimal, you have orders of 2 here. So you have a ones column, a twos column, a fours column, and an eights column. So for example, if you want to find the decimal equivalent of 10110, that would just be 0 into 2 power 0 plus 1 into 2 power 1 plus 1 into 2 power 2 plus 0 into 2 power 3 plus 1 into 2 power 4, which is 22 to the base 10. So whenever I write numbers in this format, this tells you that this number is 22 to the base 10. So it is 2 into 10 plus 2 into 10 power 0. And if I write here, this is to the base 2. Now binary numbers, because the place value is so much smaller, they sometimes tend to be very tedious if you have to write long binary numbers. And so in that case, what we do is we group 4 bits into one and write them as hexadecimal numbers, which are numbers written to the base 16. So for example, 2e16, you can write e into its 4 bits and 2 into its 4 bits, giving you the number 1110 and 0010. In the hexadecimal system, after 9, we use the letters A, B, C, D, E and F to denote numbers from 10 to 15. So similarly, now if I had a binary number of this format, I would essentially break this into groups of 4. So I would group this as 1, and then here I would place a 0 which has no value, and then when I group this, I would get this number to be 7a to the base 16, right? So hexadecimal gives you a much compact method of writing out binary numbers. A couple more terms to keep in mind as we go through digital design. A byte is nothing but a group of 8 bits. So a byte is commonly used to denote size of memories, etc. So whenever we measure size of a memory, we normally denote it in bytes. Olden times they used to use the word nibble, which is not of any use, which is basically half of a byte. A word or a digital word is a chunk of data which the microprocessor handles. And the size of the word becomes important because that is determined by the architecture of the microprocessor that's used. We'll talk about two other terms, an LSB and an MSB. LSB stands for the least significant bit, which is the bit in the ones column, and MSB stands for the most significant bit, which is the leftmost bit in the word. So when we want to represent numbers, so for example, when we think about logic or arithmetic, we always deal with positive and negative numbers. So when you have to deal with signed numbers, there are different ways of dealing with signed numbers. The simplest way of coding up a signed number is known as the sign magnitude format, in which we use the MSB for the sign and use only n-1 bits for the magnitude. So if I want to denote plus 5 to the base 10, that would be 0101, and if I want to denote negative 5, that would be 1101. So this indicates the sign, 0 or 1 indicates whether it's a positive number or a negative number, and the rest of it denotes the magnitude of the number. So in this, if you look at it, the n bits span the range of numbers from minus 2 power n minus 1 plus 1 to 2 power n minus 1 minus 1. Now the problem with the sign magnitude convention, right, is that binary addition does not work in this. That's because we have arbitrarily chosen this MSB to be the sign bit. So for example, if I do a very simple addition of minus 5 and plus 5, I should get the answer 0. Instead, I end up getting some garbled chunk. Right? That's because this does not lend itself to binary addition. The two's complement technique or the two's complement representation is a better way to implement signed numbers, and it's what is normally used. So here if you look at the two's complement, the MSB has a weight of minus 2 power n minus 1 instead of 2 power n minus 1. Right? So for example, if I have the number 0 with all ones in the subsequent bits, it is a positive number of 2 power n minus 1 minus 1, whereas a 1, which is just 1 ahead of this, becomes a negative number of minus 2 power n minus 1. So how do we generate the 2's complement? We generally generate the 2's complement by representing the positive number in binary, invert every bit, and then add 1 to the number. So for example, 2 to the base 10 is 0, 0, 1, 0. If I want to find minus 2 to the base 10, I flip each and every bit here, so that becomes 1, 1, 0, 1, and then add a 1, and that becomes 1, 1, 1, 0. So 1, 1, 1, 0 represents minus 2, and this represents plus 2. And now you see that addition works, because if I want to do a minus b, it's just a matter of taking a and then finding the 2's complement of b, which gives you a negative number. So for example, if I add 2 to the base 10 and minus 2 to the base 10, you will see that I will get essentially a 0 with an overflow, indicating that 4 bits will make it a 0. Now let's review logic gates. The most basic gate that we will use initially to do our circuit design would be the inverter or the NOT gate. The NOT gate essentially inverts the input. So y is denoted as a bar, which means if a is 0, y is 1, and vice versa. Something which is very commonly used in design, but you can easily implement this by cascading two inverters one after the other. Now the buffer essentially just follows a, if you will. So y is equal to a. Now buffer, we'll see, is used a lot when we want to restore signals. Right? So we want to bring signals back to healthy voltage levels. We stick a buffer in the chain, and the buffer will essentially do that. Then we have the basic Boolean symbols, which is basically and or. An and signal is represented as y equal to ab, and this is the AND gate, and the AND gate is high only when both A and B are high. The other gate which is also used is the OR gate, which is the majority gate, where the output is high when either one of A or B are high. Now what we see is that and OR are difficult to implement in CMOS, CMOS being a naturally inverting technology. So many a times we deal with the NAND and the NOR gates. So the NAND is the not AND gate. It is denoted by the AND gate with a bubble, indicating that the output is a complemented version of the AND. Similarly, the NOR gate is denoted with the OR with the bubble, and it's the complemented version of the OR. So in the NAND gate, the output is high for OR, is always high, and it goes low only when both inputs are high. The NOR gate, the output is always 0, and it goes high only when both the inputs are 0. So the NAND and NOR are kind of duals of each other. Two other special gates that we'd use, and especially the XOR, for example, finds its use a lot in logical as well as arithmetic circuits. The XOR gate is an exclusive OR gate, which means that it goes high only when A and B are dissimilar. That is, only when A is 0 and B is 1, or A is 1 and B is 0. When both of them are similar, the XOR gate essentially gives an output 0. And the complementary gate of that is the XNOR gate, whose output is the complemented XOR output, which goes high only when A and B are similar. So you can think of the XOR as a gate that highlights when the signals are not similar, whereas an XNOR gate highlights when the two signals are the same. Typically what we do is, when we do CMOS circuits, we go up to 3 or 4 input versions, not more than that, and we'll talk about that once we do transistor level design of gates. But generally, if you look at it, we normally design 3 or 4 input versions. If you want furthermore, we design them using a cascade of gates. And again, we look at all that as we go through this course. Now let's talk a little bit about the figures of merit of the logic gates. The first obvious one is the speed of operation. For example, if I consider an inverter, let's assume that the inverter has an input which goes from 0 to VDD. Now because the inverter flips the input, the output, when the input is low, the output is high and vice versa. However, what you see is it takes a certain time for the output to track the input. So we talk about two delays, one which is known as the falling delay, that is the delay when the input transitions high to when the output transitions 0, and the rising delay at the output, which is the flip condition when the input falls to 0 and the output rises to 1. And you see that these two are numbers which are going to be greater than 0. Now, in the most generic case, it's not necessary for these two to be equal. In fact, we will have special cases where we would intentionally make one faster with respect to the other by trading off the other for certain specific applications. Now, why are delays important? Again, no, we are not normally going to use just one gate, right? So you're normally going to think of your system as a cascade of such gates. And so you can imagine that as these gates, as signal moves from one end of the gate chain to the end of the gate chain, these delays are going to add up, and that's going to limit the speed of computation or the speed at which the output is created. Now the other figure of merit for the logic gate is the power dissipation. So remember, every time this gate is giving you an operation or is giving you an output, it is burning power, right? We spoke about two important properties, if you will, of the digital gate. One is noise immunity and one is restoration. So digital signal restoration essentially means that power is consumed to ensure that the output behaves better than the input. Right? So if you look at Y as it transitions between 0 and 1 in a CMOS gate, which is what we look at, you'll see that there is power burnt because current is pulled from VDD during the rising transition and current flows to ground during the falling transition. So every time this node switches, you're going to have current which flows from VDD to ground, which essentially means that you're going to have a power that is going to be dissipated in the system. And so the more the gate transitions, the higher the power. And so it becomes important to understand how these gates transition, how many times do you actually want it to transition, and also it depends on how much current is being pulled by the gate as well as the supply voltage. The third important figure of merit is known as the fan in and fan out. Now this deals with how many inputs can you connect at the gate. For example, how many inputs can a particular gate take? As I told you, typically when we design, we normally keep it to a max of 3 or 4, but you can always design higher provided you know what the trade-off is. So when you're comparing different technologies, for example, you want to know that you want how many gates can I connect at the input. Similarly, fan out is another important parameter which tells you how many gate inputs can I drive from the output of my gate, right? For example, if you think about an output being current, suppose I drive a lot more gates, there's a chance that the current might be divided and eventually go down, right? In which case then I will be limited on the fan out. Now in CMOS we have very high numbers for fan in and fan out, so it's not an issue in CMOS technology, but this is something to keep in mind if you're thinking about a new digital gate technology. The other values we need to worry about are the current and voltage parameters. Again, if I recall this 3.3 volt table, the voltages and the currents are going to determine the speed and the power dissipation of the gate, right? So ideally, you want smaller voltages, which means the power dissipation is smaller and the switching is faster. However, these voltage levels, the smaller they go, the noise margins get affected. So that's something you need to keep in mind when you're picking the right voltage levels. And these voltage levels also determine the kind of device you're going to use in the technology. Because the voltage level determines supply voltage, which tells you what is the maximum voltage a node can have in the technology, and also tells you what is the largest field. So when you're designing a semiconductor device, this limits the size of the device. And as I mentioned, we also talk about noise immunity, right? So we want the noise immunity to be as high as possible. Ideally, we want noise margins to be VDD by 2 or as high as possible for 0 or 1. That way, we can ensure that the noise immunity is perfect. And the last thing we talk about is the operating temperature range. So, as all of you are aware, run chips in computers, for example, or in server farms, these chips are going to be running at a higher temperature than room temperature. Right? And we want to ensure that the properties of the gate do not change at higher temperature. And so, understanding the range of operating temperature or making sure that your design works for the entire operating temperature range is something you need to keep in mind, and it's some figure of merit for a logic gate. So, to conclude, it helps engineers to have a bird's eye view of design, understanding the process of abstraction, and ensuring your design follows the basic rules of it being hierarchical, modular, and regular. We talk about binary numbers and we talk about multiple gates and digital system design. It's a good idea to go and recall all that before we go on with subsequent lectures.